Good morning, everyone. Our topic for today is all about the carbonyl alpha substitution reactions. The A position, or also known as the alpha position, the carbon next to the carbonyl group is designated as being in the A position. Electrophilic substitution occurs at this position through either an enolate or enol ion. The green portion, which has a positive sign, is the electrophilic ion. Many schemes makes use of carbonyl alpha substitution reactions. These reactions are one of the few general methods for making carbon-carbon. Next, we will tackle about the keto-enol tautomerism. A carbonyl compound with a hydrogen atom on its carbon rapidly equilibrates with its corresponding enol. Compounds that differ only by the position of a movable proton are called tautomers. Tautomers are not resonance forms. Why? Because tautomers are structural isomers. Resonance forms are representations of contributors to a single structure. Tautomers inconvert rapidly while ordinary isomers do not. Enols. The enol tautomer is usually present to a very small extent and cannot be isolated. However, since it is formed rapidly, it can serve as a reaction intermediate. Below is an example of enols. Acid catalysis of enolization. Bronsted acids catalyze keto-enol tautomerism by protonating the carbonyl and activating the alpha protons. Base catalysis of enolization. Bronsted bases catalyze keto-enol tautomerization. The hydrogens on the alpha carbon are weakly acidic and transfer to water is slow. In the reverse direction, there is also a barrier to the addition of the proton from water to enolate carbon. So here in the base removes the acidic alpha hydrogen, yielding an enolate ion with two resonance structures. Reactivity of enols. The mechanism of alpha substitution reactions. Enols behave as nucleophiles and react with electrophiles because the double bonds are electron-rich compared to the alkenes. So in the figure below, you can see that the examples, enol tautomer and the electron-rich. General mechanism of addition of enols. When an enol reacts with an electrophile, the intermediate cation immediately loses the negative hydroxide proton to give a substituted carbonyl compound. So there are the steps in doing the general mechanism of addition to enols. First is the acid catalyzed enol formation occurs by the usual mechanism. Next, second is an electron pair from the enol oxygen attacks an electrophile, forming a new bond and leaving a cation intermediate that is stabilized by resonance between two forms. Last is the loss of a proton from oxygen yields the neutral alpha substitution product as the new carbon-oxygen bond is formed. Alpha halogenation of aldehydes and ketones. Aldehydes and ketones can be halogenated at their alpha position by reaction with 2-chlorine, 2-bromine, or 2-iodine in acidic solution. Mechanism of acid-catalyzed bromination. The enol tautomer reacts with an electrophile. The keto tautomer loses a proton. The carbonyl oxygen atom is protonated by acid catalyst, which is shown here in the example 1. Here in example 2, the loss of an acidic proton from the alpha carbon takes place in the normal way to yield an enol intermediate. In the third, an electron pair from the enol attacks bromine, giving an intermediate cation that is stabilized by resonance between two forms. In the fourth, the loss of Negative hydroxide proton then gives the alpha halogenated product and generates more acid catalyst. Evidence for rate limiting enol formation. The rate of halogenation is independent of the halogen's identity and the concentration. In D3O plus and the alpha H are placed by these at the same time rate as halogenation. This is because the barrier to formation of the enol goes through the highest energy transition state in the mechanism. Elimination reactions of alpha bromoketones. Alpha bromoketones can be dehydrogenated by base treatment to yield alpha B unsaturated ketones. Alpha bromination of carboxylic acids. Carboxylic acids do not react with bromine 2, unlike aldehydes and ketones. They are brominated by a mixture of bromine 2 and PBr3, Hell-Volhard-Zielinski reaction. Mechanism of bromination. PBr3 converts to negative COOH to negative COBr, which can enolize and add Br. Reagents for enolate formation. Ketones are weaker acids than the OH of alcohols, so a more powerful base than an alkoxide is needed to form the enolate. Sodium hydride or lithium diisopropylamide are strong enough to form the enolate. Lithium diisopropylamide, or also known as LDA. LDA is from butyllithium and diisopropylamine, soluble in organic solvents and effective at low temperature with many compounds, not nucleophilic. So our table 22.1 shows the acidity constants for some organic compounds, or the acidities of organic compounds. In our functional group, so we have carboxylic acid, 1,3-diketone, 3-ketoester, 1,3-diester, alcohol, acid chloride. We also have the molecular structures of each functional group. Next is the reactivity of enolate ions. The carbon atom of an enolate ion is electron-rich and highly reactive toward electrophiles. Enols are not as reactive. Reaction on oxygen yields an enol derivative. Reaction on carbon yields an alpha-substituted carbonyl compound. Alkylation of enolate ions. So, base-promoted reaction occurs through an enolate ion intermediate. Constraints on enolate alkylation. SN2 reaction. The leaving group X can be chloride, bromide, iodide, or tosylate. R should be primary or methyl and preferably should be allylic or benzylic. Secondary halides react poorly and tertiary halides don't react at all because of competing elimination. The malonic ester synthesis. For preparing a carboxylic acid from an alkyl halide while lengthening the carbon chains by 2 atoms. So, in the figure below, we can see that the malonic ester and synthesis yields towards the carbon. Dialkylation. The product has an acidic alpha hydrogen, allowing the alkylation process to be repeated. In the figure below, we have the example. Alkylated malonic ester yields towards carbon and comes up with the major product, dialkylated malonic ester. Formation of enolate and alkylation. Malonic ester is easily converted into its enolate ion by reaction with sodium ethoxide in ethanol. The enolate is a good nucleophile that reacts rapidly with an alkyl halide to give an alpha-substituted malonic ester. Here in the figure below, the first example is the diethyl propane dioate, or also known as the malonic ester. Yields towards the sodium malonic ester, and to come up with the major product, the alkylated malonic ester. Hydrolysis and decarboxylation. The malonic ester derivative hydrolyzes in acidic and low-cis carbon dioxide decarboxylation to yield a substituted monoacid. Decarboxylation of B keto acids. Decarboxylation requires a carbonyl group 2 atoms away from the negative CO2H. So the overall conversion. The malonic ester synthesis converts an alkyl halide into a carboxylic acid while lengthening the carbon chain by 2 atoms, which can be seen in the examples below. Preparation of cycloalkane carboxylic acids. 1,4-dibromobutane reacts twice, giving a cyclic product. 3, 4, 5, and 6-membered rings can be prepared in this way. So, in the first figure, we have the 1,4-dibromobutane. Acetoacetic ester synthesis. Overall, the acetoacetic ester synthesis converts an alkyl halide into a methyl ketone. So in the figure below, you can see that R reacts to X. Acetoacetic ester and synthesis yields towards the carbon. Acetoacetic ester, or also known as ethyl acetoacetate, alpha carbons is flanked by 2 carbonyl groups, so it readily becomes an enolate ion. This can be alkylated by an alkyl halide and also can react with a second alkyl halide. Generalization of B keto esters. The sequence: enolate ion formation, alkylation, hydrolysis, or decarboxylation is applicable to B keto esters in general. Cyclic B keto esters gives 2 substituted cyclohexanones. So that's all for my topic about the carbonyl alpha compounds. Thank you for listening and God bless.